All right. So we have learned how to balance equations. We had a homework set of problems. We had to balance 3 equations. You have to have an atom inventory to show how it's balanced. You have to use coefficients to balance it. You can't stick coefficients in the formula. You can't change the formula. As we learned yesterday, once the formula is set, you can't touch this. Okay? So this one was already balanced. In this class, I expect you to give me an atom inventory even when the equation is balanced, because I'm from Missouri. Okay? For those of you listening to the video, I'm not really from Missouri, but look up the state's slogan. Maybe it'll make sense. All right. And so this is the third one you had to do. And they can get pretty complex. Okay? Well, I have people from all over look at these videos. Okay? Yes, from all over. I don't know. I've had over 4,000 hits on my channel. The last time I checked, anyway. I don't know. It didn't tell me where they're from. Now look. So we just did a quiz, and we had to do the same thing. Coefficients, atom inventory. Okay, all those are required. If you do a step-by-step process the way I teach you, not only will you have a really good chance of getting it right, but I can tell when you go wrong what you're doing wrong. Okay? Without the atom inventory and all the parts that go into it, sometimes I can't tell where you went wrong and I can't help you as much. All right? So that's what I want you to do. Now we're getting to the point where we are going to classify equations. Now there are lots of ways to classify equations. There's some classifications that we're not going to do in here. In a high school, first chemistry class in high school, at least in this state, we generally don't talk about something called redox. So we're not going to classify any of these reactions as redox. We're going to use these classifications: synthesis, decomposition, double replacement, or you can call it double displacement. Either one of those is fine. Single. Then double replacement. The only kind of acid-base reactions we're going to deal with in here will also be double replacement. And then we've got combustion reactions. And we already did Unit 10. We took that early in this class, in this semester, this quarter rather, so that we could do the ice cream lab while it was still warm. So you should already know about combustion reactions. Okay? I shouldn't have to show you what a combustion reaction is, but I'm going to give you a quick overview. All right? So let's talk about these reactions. So the first one we'll talk about is synthesis. Okay? So here's the definition that I'm going to give you for synthesis. You have a small compound or an element that combines with another small compound or element to make a larger compound. Now you're going to have to take this definition and the examples I want to show you to look at any reaction, any equation I give you, and figure out whether it's synthesis or not. You're going to have to pick out whether any equation I give you fits one of these 6 classifications. Okay? So a small compound or element combines with another small compound or element to make a larger compound. So here's one example. Okay? Here's hydrogen gas. It's an element. It's a diatomic element. Remember we did this in the last unit. There were 7 diatomic elements you needed to know about. So this is the elemental form, the most common elemental form of hydrogen, the most common elemental form of oxygen. So this is an element too. We're putting 2 elements together to make a larger compound. And so this is synthesis. Okay? Here's an example of 2 compounds, 2 smaller compounds that we're going to put together and make a larger compound. You should recognize this one by sight. Its name is ammonia. This is just another way of writing water. HOH and H2O mean the same thing. And then they can form a larger compound called ammonium hydroxide. Although in real world terms there may not actually be such a compound. You have an ammonium ion and a hydroxide ion in a solution, which is what aqueous means, but it never actually forms ammonium hydroxide as a separate thing. That's just kind of an aside. You don't need to know that. Okay? If you wrote NH4OH aqueous, every chemist in the world will know what you're talking about. Okay? Any questions about synthesis? So two smaller things combining together to make a larger thing, that's synthesis. Okay? It's kind of like fusion when we're talking about nuclear equations. Okay? If you put together two smaller nuclei to make a larger nuclei, in nuclear equations we call that fusion. But if we're talking about chemical formulas, then we're talking about synthesis. Okay? Alright. I'll move on now to decomposition. How many of you in here play the piano? Nobody? One, two people? You can? Okay. If you think of a composer of great renown, the world's most famous composer for piano music, who would you think of?
Mozart.
Mozart? Actually, he didn't play the piano. He played, what was it called? No, did he play? He might have played the violin, but I think he was mostly a keyboardist. But the piano hadn't been invented, I think, in his time. Clavicle, that's what I was trying to think of. Yeah. Huh? Yeah, Bach mostly played the organ. He wasn't a piano composer either. Beethoven. Okay. All right. So, where's Beethoven from? Germany. He's buried in a vault. Yeah. They have it's a huge, rock building sort of. You didn't hear the story about that?
Nope.
So this guy goes to the cemetery where Beethoven's buried, and he starts hearing music. Piano music. You heard this?
No, keep going.
So he walks around, he tries to find the music, and sure enough, he comes to this big, ornate, not ornate really, I mean it's ornate I guess in a sense, but anyway, it's made out of, I think, limestone, but he's hearing piano music. And he looks around, there's no speakers or anything, it sounds like it's coming from inside. And lo and behold, the door's open. It's like cracked open, So he opens the door and he goes inside. There's a guy there in, what was it, 15th, 16th century, whatever, clothing and long hair, and he's sitting at a piano. And he'll play a few bars and he'll stop. And then he would erase some of what he composed. And then he'd play a few bars and he'd erase some more. And he asked the guy, "What are you doing?" And he says, "I'm decomposing." Okay. So, decomposing is undoing stuff, okay? If you're a musician, you might understand what we're talking about. So, composition is making a piece of music, right? Writing a piece of music. So he was undoing his writing a piece of music. So, decomposition is undoing stuff, okay? So a compound that breaks up into smaller compounds or elements, that's decomposition. Okay? And everybody decomposes when they're put in the ground. Alright, now, so here's an example. Hey, does this look like something you've seen recently?
Yeah.
No. Really? Does it look similar somehow? Does this one look like that one at all? Come on. This is the opposite of that. This is putting it together. This is undoing it. Yeah. Do I have a baggie? Yes, I have a baggie. No, you cannot. Yes, I can. I'll give you one in a little bit, okay? All right. I can't believe she asked me that right in the middle of a lecture. God. Okay. I know it. All right.
You need to apologize to the people that watching that video.
Why?
Because as a U.S. American citizen, Nelson disrupted.
Okay. So notice we have a larger compound breaking down into separate elements. Okay, this one is an example of a larger compound breaking down into smaller compounds. You can break a larger compound into a smaller compound and an element. Okay, that's also something that can be done. Or in the case of synthesis, you can have a smaller compound and an element making a larger compound. Okay? This reaction right here happens every time you open up a soft drink. That's part of what's happening right there. Okay? So soft drinks fizz because you dissolve CO2 in the soft drink and you put it under pressure and it forms this in the solution. Once you release the pressure, a lot of these things become these two things again. So decomposition occurs every time you open up a soft drink. Or for that matter, a bottle of wine or some other fizzy drink.
Oh, he said wine, they pop bottle.
Okay? Got that? Anything with fizz in it goes through this decomposition. But if I pump CO2 into liquids, then I get this. So I can make the reaction go the other way. Okay? All right. Let's look at single replacement now. Okay? Single replacement. So replacing something means you put something in place of something else, right? Yes? If I were making cookies and I wanted them to have fewer calories, what would I replace the sugar with? Splenda maybe, okay? So that's replacement, isn't it? All right. So single replacement means almost always single replacement is an element that's by itself that replaces an element in a compound. An element that's by itself replaces an element in a compound. Almost every time that's what it means. So I'm going to show you an example now of a single replacement reaction. Okay? So here's a single element. Okay? So it's by itself. It's not combined with something else. And it's going to replace a part of this formula here. In fact, it's going to replace the part of this compound, I said element, it's going to replace this element in a compound that it is like in the sense that it's a metal. This is a metal, that's a metal ion. So metals replace metal ions in single replacement reactions. Halogens replace halogens in single replacement reactions. Tyler, come here a minute. So the zinc replaces the antimony, and look, zinc's joined up with what the antimony was joined up with before.
This is mine?
I want you to just look at it. Put it back down when you finish. Okay? That makes sense? Alright. Now that's pretty simple. Okay? Does everybody understand what we mean by single replacement then? And the zinc then joins up with the nitrate here and becomes zinc nitrate. The antimony ends up by itself. Alright? So, maybe to help illustrate this idea, Let me tell you a little story. Okay?
What was that for, though?
What was that what for?
That.
I'm just making a point about your behavior just a moment ago that could result in this.
That was one.
I'm thinking about it. Okay? All right. So let's say that instead of this being zinc, that this is Julia. Okay? And instead of this being antimony, let's say this is Caitlin. And the nitrate here, let's say it's Zane. Okay?
Let's go, Zane.
So, Caitlin and Zane go out on a date.
Perfect.
Alright? And where they go, they happen to just run into Julia. Well, Julia really likes Zane. Cat bite. So, Julia kicks out. Well, we got two Julias, I'm sorry. Julia Gibson. Okay. So Julia pushes, Caitlin away here, and guess who ends up together? Julia and Zane. Okay? And poor Caitlin goes home alone. Alright, you get the point? You get it?
I'm talking about.
Okay. So that's single replacement. Got it? Alright. Let's go and look at double replacement now. Oops. Wrong thing. Here's double replacement. For those of you still writing, I'll leave it up there. And here's double replacement. Two-part compounds switch their parts. What test? No, I haven't done it yet. I'm working on them, but I haven't done it yet. Huh? I don't have to? I thought most people were thinking they did good. Alright, so two-part compounds switch their parts. Okay, so here's an example. Here's a two-part compound. A cation and an anion. Positively charged particle, a negatively charged particle. Silver has a 1 plus charge. The nitrate here on the end has a 1 negative charge. Okay? Here's a two-part compound. What? NO3 is nitrate, yes. Here's a two-part compound. Calcium and chloride. Calcium is 2 plus, so you need two chlorines to balance that out. They have a 1 negative charge. The chloride has a 1 negative charge. But it's a two-part compound. And what you end up with are two-part compounds.
On the second, after the air well, is that AgCl solid?
Yes, that's a solid. Okay? So here's what's happening. The front part of this compound joins up with the back part of this compound, and you end up with Ag and Cl together to make this compound. And Ag has a 1 plus charge and Cl has a 1 negative charge, so 1 and 1 makes a balanced compound. Then the front part of this compound joins up with the back part of this compound. So the calcium joins up with the nitrate to make calcium nitrate. Calcium has a 1 plus charge, nitrate has a 1 negative charge, so I need two nitrates to give me a balanced or a neutrally charged compound. Okay? Remember, front parts are always front parts. So silver always remains in the front because it's a front part. The positive ion always goes before the negative ion. Calcium is a front part, so it goes in front of the nitrate. Positive parts are always in front of negative parts.
So nothing goes with potassium?
Nothing goes with the calcium? Yeah, nitrate goes with the calcium. See, calcium and nitrate? This is double replacement. The front part of each compound goes with the back part of the other one.
How come the NO is after the calcium then?
Because the NO is negative and the calcium is positive. The front part here, this is calcium is the front part of this compound. If it's the front part of this compound, it'll be the front part of this compound. It joins up with nitrate, but you don't write NO3 parentheses 2 and then calcium, because the calcium always stays in the front. Front parts stay front parts. Okay? Pants always go on your legs, not your shirts. Okay? Front parts stay front parts. Got it? Wear a hat on your head, not on your feet. Front parts stay front parts. I don't even want to hear it. Okay? Alright. Let's talk about acid-base double replacement. Now, I've combined those together because in this class, the only kind of acid-base reactions we're going to be dealing with will be double replacement reactions. Okay? Acid-base double replacement. We already know what an acid formula for this class at least looks like. How do you recognize a formula for an acid? Has an H on the front, right? Okay. So the only thing you need to know now that's kind of new, because it's already double replacement like this one up here, but you need to know how to recognize a base. The only kind of base we're going to deal with at this point in time is called an Arrhenius base. An Arrhenius base. ARR, like what a pirate says. A female chicken. Hen. R, hen. You, in the subject of a sentence. I. And all of us in the room. Us. Arrhenius. Okay? Alright. Here's an example. We got an acid because it has hydrogen in the front. An Arrhenius base always has a hydroxide. One or more hydroxides. Okay? This is actually an Arrhenius acid for that matter. At this point in time in the semester, we are only dealing with Arrhenius acids and bases. All the acids we've learned about so far are Arrhenius acids. Okay? So if we have a hydrogen in the front, it's an acid. If we have hydroxide in the formula, that's OH, it's going to be a base. It's going to be that's an Arrhenius base. And here's something that's a little bit new. Well, let me talk about the double replacement part. The hydrogen on the front joins up with the OH on the back of this one to make water. The sodium on the front of this, on this particular base, sodium is in the front. On this particular acid, Br is on the back. This is the acid anion here. They're going to join together. Okay? And Tierra, notice the front part stays the front part over here. So, here's something new. The product of an Arrhenius acid-base reaction, other than water, is a salt. That's the definition, for chemists at least, that's the definition of a salt. Huh? For a chemist, the definition of a salt, not a salt like the military assaults a hill, a salt, okay? The definition of a salt to a chemist is the product, other than water, of an Arrhenius acid-base reaction. Sure you do. It's down here at the bottom. I'll show it to you in a second. Okay. Alright. Arrhenius acids have hydrogen in the front of the formula. That's what we've learned about already. We've learned about acids having hydrogen in the front of the formula. So in this class, I'm just telling you now that's an arrhenius acid, okay? What pirates say, female chicken, you in the front of in the subject of a sentence, and all of us in the room. Arrhenius. Okay? Arrhenius bases have hydroxide in the formula. And then I also said salts. Those are what is formed by the reaction of an arrhenius acid and an arrhenius base other than water. Okay. So if you have hydrogen in the front, hydroxide in the back, you're going to form water and a salt, and that's an arrhenius acid-base reaction. It's an acid-base and double replacement reaction. Okay? Oh, it should go on the outside of a bracket if I'm showing the electrons using Lewis dot formulas. Okay? But the formula just for hydroxide is OH negative. Now, if you look on your test references in the common ions, it's kind of a simplified version of what you're talking about. Okay? Let's see hydroxide. Here's hydroxide right here. OH negative. What you're talking about, okay, what you're talking about is when we do Lewis formulas, our Lewis dot formulas, this is a bracket and a negative charge outside of it. And that's true if we're showing the electrons. Okay? Okay, so let's talk about combustion. Now, we've already covered Unit 10. We took it early so we could do the ice cream lab before it got cold. Okay, Unit 10 was about thermochemistry. And so, combustion reactions are covered in thermochemistry. So you should already be able to recognize a combustion reaction of the type we'll learn about in this class, or we have already learned about in this class. Okay? In this class, we use only the simplest type of combustion reactions. Now, if you don't remember those, get out your notes for Unit 10, or go back and look at your email, because I sent those notes to everybody. Okay? A combustion reaction starts with a hydrocarbon fuel. This just happens to be one kind of hydrocarbon fuel. Any compound that is made of only hydrogens and carbons is a hydrocarbon. It's a fuel because we're reacting with oxygen. Okay? So a hydrocarbon fuel reacted with atmospheric oxygen, producing water, and because of the heat, it'll be steam, be a gas. It'll produce water and carbon dioxide. Yeah, all these are G's. Gas. These are all gases. Alright? So we did a lot of calculations of heat released in the combustion part of Unit 10 already. You should recognize a combustion reaction of the type that we deal with in this class. Okay? So I shouldn't have to explain that much further. Okay? Time for you to practice.